Okay, well, good evening and happy to have you all here. Thanks for the attention. The intent of creating a series of talks was actually driven by the fact, and the defect is the documentation we have, which is mostly still the Linux CNC documentation, documents just about everything on the periphery of the product, but is pretty much silent on how things actually work internally. There's practically no usable developer documentation or structural overview. So we discussed this on an issue for a while, and then it came out, we'll do a series of talks. So, and I chose the first one to be the interpreter, because it's actually a very good cross-section theme, and to tack on other themes later on. The second one, which I guess we'll schedule for today in a week, will be about the CNC stack all working together. So what happens when you enter MDI command? How does that percolate down all the way to the hardware? And if a pin gets wiggled, how does that get back to the UI? So that's going to be a more holistic view. We'll touch on some of these themes today. I'll postpone some of this until the next presentation. I'll present to everyone. Okay. You still can't see me, I guess. I can. Okay, I don't see me, but that's fine. So that's the first unit in a sense. It's about understanding flow and how things fit together. This is not a code crawling exercise. There will be several links in the presentation. Every time you see an underlined link in the code or in a listing, you can actually click it and it will take you to the GitHub repo or to a relevant website, pointing to or point to an algorithm or a piece of code which is being referred to in the talk. So feel free to ask questions anytime. Maybe post them to the chat window, and I'll try to answer them after every slide or so. And we'll do a question and answer at the end of the talk. I'll also at some point do an interactive example. Anyway, so let's start. So the confusion which newcomers to the which try to understand MachineKit or Linux CNC internals is pretty much depicted by this wonderful XKCD cartoon. So today we'll start at the electric eel in the middle here, and we'll try to remove some of this confusion here. So as an outline, what I plan to do, just touch upon very shortly what interpreters do. Most of you probably have used, surely have used interpreters, so that's just a recap. We'll work with a specific incarnation of the G-code interpreter called the RS-274 binary, which is basically there for testing and exploration. We'll try a couple of example G-code commands and see what happens then. Armed with that know-how, we'll review what the G-code interpreter's tasks actually are and how it fits into the rest of it, in particularly to the API right underneath the interpreter, which is called the canonical API or canon API. Hi, somebody came in. Hi, Cristiano. Hello? Okay, now it's gone. Thank you. um, we'll review the functions of the canon layer, uh, and then we'll get back in history because EMC, or the precursor of Linux CNC and MachineKit, is actually quite old software. Goes back to the Reagan era, and we'll review on how that legacy execution model, which stems from that time, actually shows through in the software until today. And we'll review on what steps have been done to improve the situation, namely adding look ahead, and how that plays in some of the um, um, a bit hard to understand features of the G-code interpreter and the behavior, which sometimes raises question, namely what is a queue buster and how does that play with the execution model. So armed with these foundations, we'll review on how the pieces are plumbed together in two specific chains, namely the motion control chain, everything what happens from a G-code command or a G-code file down to actually driving help ins and eventually motors, and the feedback pass. So that's the motion chain. We'll review that. And the other one where the interpreter plays a role is the preview pipeline. With many UIs, you get a preview. Once you open a G-code file, you get a preview on a screen depicting the toolpath. Well, that comes from an interpreter run, but it obviously doesn't move the machine. So it's a separate run, which just happens when a G-code file is opened. And we call that a preview pipeline. And that we'll review on how that plumbs into the rest of the system. That's about where I'll stop the dose for today, because that will be quite enough, I think. We'll do a question and answer, and eventually, maybe if somebody wants to take on a task, or if I can motivate somebody, I will point out some of the issues in the current code base and point to projects which could be taken on to improve the situation. Some of them are quite pressing, actually. Anyway, so that's roughly the stuff which I would cover today. So let's jump into it, into investigating what we do next. We'll jump right into it, and well, just to set the stage, what does an interpreter actually do? Well, it's basically a loop of reading a unit. Let's call it a line for now. Not every language is line-oriented, like Python, for instance, or but many are. G-code is, but also, for instance, BASIC or so forth. So that's quite, so read a line, then analyze it. In computer science, that's called scanning and parsing, extracting the lexical tokens, making sense of the syntactic structure. And if the sentence makes sense somehow, then actually execute it and print a result if there's a value to return, or else complain. So, well, that is not something particularly new. That's just a recap. And there's nothing new here also with the G-code interpreter itself. If you look at it in a Python example, we can recap these steps. The reading step, the reading phase is indicated by a prompt. We type some nonsense, and we're properly being barked at because that doesn't make sense. If we enter something which actually makes sense, it parses it behind the scenes, it executes it, and prints the results. So that is the good case, if you will. And then the whole thing repeats. So that's a very fundamental structure common to all interpreters, called the read-eval print loop. Okay? And we also find that in the G-code interpreter. Now, before we actually experiment with it, we'll cook up a little example program. It's really trivial. It's just a rapid move, a feed move, another rapid move. The whole thing is in relative mode, and it executes with feed 100. So it's really just three segments. Now the interesting part, let's assume the interpreter thought when it started executing that program, the machine has three axes, X, Y, Z, and everything started out at 0, 0, 0, just for simplification. Now, as the interpreter reads each line of that program, it can actually predict what the position at the end of the move is, at the end of the execution of the next line is. So it's clear that after line 20, we're at 10 minus 520. But that's a very important property. That point is called the current point in the interpreter code. And it's a fundamental assumption that the interpreter always needs to know where the machine actually is. We'll come to that back later because it's a very important fundamental property. Okay, we're not needing it right now yet, but we will. So, okay, what we do next is actually run a demo, and I'll switch a screen share here now. I'll actually run this. Let me do this. Share the screen. I think this is it. Yes, this should be it. That's a standard machine kit install. There's nothing exciting here. What I'm doing here is start the RS-274 binary, which I'm not sure if that is a very well-known one. It's existed in the code base for a long time. It's the so-called standalone interpreter, and it's used for exploration and debugging. Very few people actually use it because they use the interpreter which is packaged up in a complete configuration. But sometimes to explore it, it's easier to use this standalone interpreter to figure things out. So let's do that and start it. And what we see here is that it creates a couple of lines of output, each one of which relates to a command which the interpreter passes downstream towards the motion pipeline, towards the trajectory planner and the motion plan out. This is basically just an initialization sequence. It just says, please interpret everything in millimeters. We're currently not using offsets, we're not using rotation, and we're using a certain feed reference. So that's just a standard initialization sequence. Now I'm going back and will paste in the program. I'm sorry, just let me go through the flow. So each line of that, which we see on screen, actually corresponds to a canon API call. Canon stands for Canonical Machine Commands, and it is, if you will, an abstract machine, which can be moved by feed moves, by rapid moves, by arcs, by lines, and then there's a whole lot of supplemental commands like turn on mist, turn on the spindle, turn off the spindle, do a tool change, a whole lot of them. Maybe 40 or 50 calls. It's not very complex. That's called the Canonical Machine API. And by the way, in the slides, if you click on the lines in that slide, it will take you to the definition of that Canon API call. Okay. The machine kit code base has actually several Canon implementations, and that's probably a little bit confusing. They all share the same API, which is in the Canon, defined in the canon.hh, file, which is linked in the slide. And what I'm doing here is start the RS-274 binary, which is the so-called standalone interpreter code. And I'm going back and will paste in the program. let's go back here for a second. Stop the screen share. Sorry, screen share. I'll go back to the slides. Where are the slides? This is it. Okay. There are actually several canon layers, and they serve different purposes. One is for actually driving the machine, and that creates has quite a substantial functionality. Others are like the one which we are using here in the standalone interpreter, essentially just wrap us around the calls and output the parameters. The implementation behind this so-called standalone canon API is trivial. That's each one is like 5 or 10 lines of C. So we're not going into detail. That's just debug output, saying I was called with these parameters. Big deal. And a third one is used for generating preview, because we will be interested in the feed and rapid moves and arcs, so we can actually draw on the screen a wireframe of what is going to be executed by the machine later on. So that's a third canon layer. And the way this fits together in the code base is which canon layer is used is unfortunately a link time decision. So once the program is linked together, you need to know it's either for this or for this canon, that canon layer. That's not particularly flexible, and I'll come back to at the end on project suggestion, because that is a very unfortunate decision which has to go. The interpreter itself is found actually in several places in the code base. Might be known, might not be known. I'm just recapping them in here. The one which we just saw is this exploratory tool, RS-274, but it's not used to drive a machine. The ones which actually do something are in the so-called mill-task daemon. That is basically the controlling process for the CNC stack, and we'll go into more detail in the second talk on that. Also, there are instances of the interpreter linked into two G-code modules, into two Python C extensions, namely what's called the G-code module. That's the stuff which is, if you have ever read up, for instance, on Axis code, that's imported with import G-code. That is for generating preview commands in a Python user interface. And then there's something which Alex and I have come up with, that is for supporting the remote UIs which we have created, and that's called preview module, and that's imported with import preview. So to summarize, it's a link time decision. We have several canon implementations for different purposes, and you find several incarnations of the interpreter throughout the code base. Just to finish, sorry, I actually clicked the link here. Just to finish our example, what we're going to do next, I'm going to paste. I just used, believe me, on the actual interpreter, the same sequence appears than you have in the slide here. I'll do it nevertheless here. Okay, and switch it here. Let me restart that so we can see it all from the beginning. So I paste the little program here, and we got a few more canon calls out of it. Two of which are interesting because they are moves. The so-called straight traverse, that's a rapid move, or a fast jog, if you will, from A to B. And the other one is a feed move, which is controlled by the feed rate. Those would actually create lines in the UI, and they would be used for moving a tool rapidly or actually doing a cut, for instance, in a mill. Okay. So much for the example. So again, if you click on any of these links, it will lead you to the definition of the canon API call. So, and each line corresponds to one call of that canon API. For instance, setting the feed rate, F100 calls the canon command set feed rate 100. Well, that's not particularly complex. So in general, there's almost a one-to-one correspondence between a word in G code and canon API calls. So it's a quite direct relation. Good. So basically, what the interpreter does is parse and analyze a block of G code, and then issue a set of canon calls. Okay. So in the next slide, we'll look a little bit on what canon actually does. Okay. In terms of interfaces, the whole thing is C++, but if you read it, you would think it's Fortran from the late 60s. It's all uppercase function names, for instance. Very bad style. Anyway, and it doesn't use capabilities C++ provides, unfortunately. But technically, from compilation and linking, it's a C++ API. It provides movement commands, like the ones which we just saw, the feed and rapid, and all the other actions which we already touched upon. So you see that the whole thing is pretty much oriented towards a mill, towards cutting sort of heavy metal and things which have a spindle. Although it can be used to drive other machines, like for instance a lathe, but the command set really shows it was designed with a mill in mind. Okay? So what does happen in the canon layer, which drives the motion tool chain, which we'll revisit in a few slides as it all fits together from now. There are a couple of things. The important ones are handling of offsets, the G5 and G5X and G92. Offsets are handled in the canon layer, so they're remembered there. The interpreter code was not aware of offsets, so it was tacked on later on, and debatably that functionality was moved in the canon layer. Also, table rotation of a mill, that was tacked on later as well. It's also handled there. A key function is there in canon is the conversion between machine units, whatever they are, and whatever the G code is set to, which is either inches or millimeters. So that state is recorded, and canon evaluates it to convert between the units. Sometimes that goes wrong, but that's where it happens. Now, as for motion commands passing through the canon layer, there is some checking of boundary conditions, in particular velocity and acceleration. But the real stuff actually happens downstream in the trajectory planner, which we'll have a closer look next time. The one major functional unit in the canon layer is naive cam detection. Not sure if this is very much familiar. This is about line simplification. Originally, when much G code was hand programmed, you typically would have actually quite long cuts and RX spirals and so forth. But nowadays, much of G code is generated by CAM packages, and in many CAM packages actually approximate curves by emitting by emitting very short segments. So you get a lot of very short lines, and that puts some stress on the motion pipeline, as we will later see, and has led to further developments like look ahead. Sometimes it's possible to do a trade-off between accuracy and speed. And naive cam detection is about providing tunable knobs for exactly that trade-off. So we have, and the last functionality which we have there is retrieving the actual machine status. Remember, we said the interpreter at any time needs to know where the machine, the current point, actually is. Now, if it starts up, the first thing it does is interrogate the canon layer and say, where the hell am I? So that's the feedback chain from the machine. That's a very important one. So that's the more those processing functions are in the motion pipeline instance of canon, which I call EMC canon. The source file is called emccanon.cc if you look through the code base. That is really only used in the motion pipeline. The alternative canon outputs, if you will, for preview or standalone canon actually do not use any of that. In the case of preview, it's not needed. In the case of the standalone canon, that was actually a design deficiency, because you cannot actually see, for instance, what the offsets or naive cam detection for actually does to the line segments. The RS-274 binary will not show you what the motion canon layer does with naive cam detection. So some of the decisions were very poorly made. They go long backwards, but that's how they are. So downwards, or towards the using entity of the canon layer, towards the machine, the trajectory planner, what canon does is emit command messages, basically C or C++ structures filled in with a command type and parameters, and off they are sent to the next processing step. Very similar scheme we do use in the case of remote preview, because the interpreter which generates the preview display executes where all the rest executes, the real-time task and so forth, but the UI is somewhere else. So we need to send essentially a display list of the wireframe from the RT host towards the user interface. And so that it is also basically a list of C structures or protobuf messages as we use it now. In the legacy case, if you're using Axis, for instance, it works a little bit different. There's no need to send these messages, but we'll revisit that Python module in a little bit more detail later. Or in the trivial case of standalone canon, it just emits text output. I got called with parameter such and such, and that did what my name was that, and this is it. So that's what we just saw in the screen share. Okay, clear so far? No complaints, so I'll continue. It's important to note that the Canon API is not aware of G-code. It's not in any way tied to the RS-274 NGC language, which means you can actually use any language, provided you you call that Canon API and generate Canon commands. I'm pointing to that specifically because that was always there, but it has barely been used. If you want to look at an example where that is the case, there's a Python module called author.pp, and if you click on the link, it will take you to the MachineKit GitHub repo and display that file. And you'll see the correspondence to what we discussed before at the Python level pretty directly. So that's a short overview of the canon layer. So we're done with that. Now let's turn to the interpreter proper. We've viewed the G-code program. We have viewed the canon layer below. Now, what's the interpreter's task really? First, maybe I'm not sure if the term is commonly known. I'll use the term polyline for a toolpath. That's essentially a connected sequence of either a line, an arc, or a spline. That's the common term in computer graphics. In this space, it's usually called toolpaths. Now, what the interpreter's job then is read a block of G-code. You remember the read-eval print loop. To parse it, check it for syntactic and semantic sensibility, and then emit what is called an intended or ideal toolpath is according to the program. It emits the path for the tool tip, and if it's a more than 3-axis machine, it might actually emit the tool orientation. So that could be up to 6 axes. We have 3 more axes available to convey, and those are used for rotary tables in the X, Y, and Z direction. But at that level, we're talking a polyline. Hi, Darren. We're talking a polyline which is emitted, and it's the idealized toolpath. So that's the line and arc and spline segments. And along with each segment, you have the intended feed, what you gave with an F word. Okay, let's call it the feed word, like F100 in our example. Or the implicit as a rapid with a maximum speed the machine can handle if it's a G0 command or a rapid a straight traverse. Okay, so it emits an ideal toolpath with an intended feed. That doesn't necessarily mean the machine actually moves at that speed. That's a different kettle of fish. But that's what it generates, and that's what it passes on to the canon layer through the API, which we just reviewed. The straight traverse, straight feed move calls did exactly that. They convey segments of this polyline. So conceptually, it's a connected path. Now downstream in the processing pipeline within Canon, but particularly in the trajectory planner, this polyline becomes subject to optimization at one hand, but also limitations. For instance, machine limits, okay, like maximum velocity acceleration or jerk limitation. So that is why the output doesn't exactly match the intended tool in terms of speed. The machine limit kicks in. But that is neither handled at the Canon, at the interpreter, nor at the Canon layer, only with a very cursory range checks. That is handled in a trajectory planner proper, which we'll not cover today in detail. So that polyline is optimized. The velocities are adapted according to the machine. Maybe the shape changes if blending comes in, but that's not something we'll deal with right now. Important to understand is the G-code interpreter is a Cartesian space affair. It has no clue of kinematics. It's all in Cartesian space. So it's x, y, z for the tooltip, and it's x, y, z for the tool vector. This is it. The interpreter has no notion of a non-trivial kinematics machine. That is handled downstream in the G-code in the back end, just between the trajectory planar and the motion being played out. That's where the kinematics comes in. But motion and consequently also the canon layer have no clue about kinematics. So it's all Cartesian, which explains why if you have say a non-trivial machine, well, guess what? There is no way to move a joint in G-code because it was designed with Cartesian space in mind. So there wouldn't even be available words to do so, even if one could. So generate polylines, idealist, an intended ideal path, an ideal feed, and it all happens in Cartesian space. There's practically no optimization whatsoever of the path in the interpreter proper. I'm saying it again, it must be able to predict the endpoint of the next move at all times, because we're going to need this very soon. And, well, any adjustment to either the executed velocity of the segments or the shape of that toolpath happens downstream, might happen downstream in the trajectory planar if limits are hit. So the ideal toolpath, as you express it in G-code, may not exactly match what the machine actually does later on. Okay? So that's a top-level view of what the interpreter does. Okay? Now, we've looked at this, what these pieces, canon and interpreter, do quite in detail already. And what we'll do now is a time warp. We'll go back 20 years, okay, to the very early model of EMC, which was the enhanced machine controller, the precursor of all the software which we're using. And at that time, actually, what these CNC machines were driven by feeding it paper tapes. Okay, so auto mode in the user interface actually was meant feed this a tape. And why am I mentioning this? Well, it still shows. So it makes sense to actually discuss what the original execution model was, maybe also to understand some of the limitations of the current code base. The original design was a single block execution model. Again, we have this read eval print loop. It reads the next block from the paper tape. It emits the canon commands for that particular block, and then moves the machine. And when we had no error conditions, it would proceed to the next block. Okay? So the original model of EMC1 was we stare at a single block only, okay? A single line segment or an arc. Now, if you imagine the machine moving now, what does that mean if the machine comes to the end of a block? Well, there isn't many options because we don't know what's coming because we haven't read the next block yet. So the only option at this point is we need to stop at the end of the current segment. And once we've read the next block, well, we'll have to start again. Okay? So that is a consequence of the interpreter originally only looking at one block at a time. Now let's look at the motion and what that actually means in terms of velocity and acceleration. Let's assume we have a simple path, the two line segments connected joined in a sharp corner. Okay. So with a single block inspection model, the trajectory planner would ramp up to the maximum speed. We'll have a cruise phase, and as we come close to the end of the current segment, it actually needs to decelerate and come to a full stop. Okay, and once we have the next segment pulled in, the game repeats. It all again ramps up to maximum speed. We have a cruise phase, and we decelerate to the end of the towards the end of the segment. But at both ends, we come to a full stop. Now, if we look at what that means in acceleration, that's idealized, of course. There's no such thing as infinite jerk machines, but we have that is the acceleration pattern produced by that trajectory. Okay, so now that stopping in the corner, that is nice if you do want to have an exact move, right? But it is detrimental if you don't care on if the corner is cut very, very precisely. If you do, for instance, roughing or have some processing step, which is where you would prefer speed over accuracy in the corners, then that clearly is not an optimal solution. What we really would like to have is actually something like this. What we want to have is a trade-off option. If we're coming close to a corner, we'd say, well, shucks, we'll not go right all the way down to the corner and stop, but we'll do a curve. So we'll do a smooth blend from one line segment to the other. We enter the curve tangentially, keep until we have the new orientation, and exit the curve tangentially as well. Pass it to the Is this? I'm just seeing that there is there are issues with sound. Could you give me quick feedback if sound is okay? Okay. Okay, fair enough. So that's what we want to have, a trade-off. If we could keep going and I'm not sure what is going on here. Anyway, we would want to keep going and trade off speed versus accuracy. Note we gain something. We don't decelerate to a full stop. What we might go into a lower speed in the curve to limit tangential acceleration. So actually, that cut will be faster. Okay. So we can trade off speed versus velocity, and we can actually improve or reduce the load on the hardware because that is smoother than a bang bang in the corner. It creates less jerk. So that's what we would like to have, because if we go back here and assume for a second the segments which we have come from some CAM package, for instance, OpenSCAD or so, or SCAD there too. Well, the stuff the 3D printer guys are using. Actually, I think it's Slicer which creates these short segments. If you imagine all these segments are very short, then you get a lot of acceleration, deceleration ramps here. But probably the machine will not be able to actually reach the speed of the maximum velocity for the cruise phase. It would just keep accelerating and decelerating for each of these little small segments. So if you have long segments, well, and long cuts, it might be acceptable. But if you have a CAM package which does lots of short segments, then that model is the pits. So then we really want the other model where we can do blending and keep up to speed. So great. Now what does that mean? Well, if you look at the curve here, the curve actually starts before the end of the segment. That means the decision to enter the curve needs to be taken before the end of the segment. Well, obviously, what must happen in our motion pipeline is that more than one segment is being looked at. Otherwise, an optimization is not possible, because we need that information that a segment is coming here in that angle, and we need it probably somewhere around here to still be able to make the decision to enter a blend here. So this means we need to do something in the execution model of the interpreter, because that single block execution model will not get us acceptable performance, especially with CAM packages. So that look at the current block, execute, move the machine, look at the next block, that doesn't scale. So what we need is we need a scheme where the interpreter looks ahead segments, maybe actually many, and in many commercial controls that's actually configurable, like I think maybe up to 1,000 what I've seen or so. And consequently, we don't have a single currently executing block. We do now have a queue of segments which are essentially live between the interpreter and the hardware, and the software between the motion pipeline can now investigate that queue and do the optimizations. So reading ahead of the currently executed command is a precondition that we can actually do any optimization on the motion in the motion pipeline. Okay, so reading ahead gives us a queue of moves, maybe many. Maybe in the case of the way the machine kit task program is designed, it actually will do, it will read ahead until it runs out of memory, which is not a very bright thing to do, but that is the cause why you've seen these out of memory errors on embedded platforms. It is not particularly bright about read ahead. So it just keeps reading and generating, adding segments to the queue until it bombs, because there is no swap space on an embedded system. So fine. So we have to deviate from that one block at a time model to the interpreter needs to be ahead of the machine. We get a queue, and now we can play games on the queue and optimize things. We can change the shape. We can insert little blends. We can do this naive cam detection stuff. So, but what that means, the interpreter is ahead of the moving metal. Okay, what the interpreter sees and its variables have nothing to do with what currently moves the machines. Those are separated by time and the motion queue. Practically always it's ahead of the machine. We'll come to the cases where it cannot do that in the subsequent slides. And in the particular case of our example program, which we looked at in the beginning, where it was perfectly possible to predict the position at each step, the interpreter could execute the whole program, dump all that canon commands into a queue and stop, and the machine hasn't even started moving yet. That is fine. Okay, so as long as the interpreter can predict the machine position, it can run ahead, and you could actually store that stuff in a file and run it later on. It's not important. The key property is it needs to be able to predict the position. So and that is sometimes that crops up in user interfaces because it's a very hard to understand concept, the differentiation between read ahead time and motion time, because you give some command to the interpreter, and the stuff, the variables, the state it sees does not exactly correspond to what the machine is, but to something which is further ahead, further back in the motion pipeline because of read ahead. So that is a concept, makes it conceptually a little bit difficult, but we need it for performance reasons. So that's where we come to define the term read ahead time or motion time. Okay, motion time is everything what moves, changes current held pins. For instance, the commanded position, commanded velocity, and so forth. That is motion time. Whatever the interpreter thinks that what the current point, the current tooltip is at, that is read ahead time. And since we have introduced read ahead, that does not concur anymore. Okay? And for trivial programs like we had, it might be actually completely decoupled. Interpreter finishes before even the machine moves anything. That's the first noise. Now, in terms of optimization, I already alluded to that, so I will skip most of it. The method employed in the canon layer for naive cam detection rests on a classic algorithm in computer graphics. It's called the Douglas-Bücher method. Basically, that trades off the number of segments versus pass accuracy. And that's in a canon layer. And the other transformation, which we already alluded to, that is blending, and that is in the trajectory planner proper. Both are actually controlled by G-code parameters, but the interpreter just takes these G64 and G61 words and passes them down to canon because it has no idea what they mean. It just passes them to parameterize the processing further down in the motion pipeline. The interpreter per se has no clue, okay, what these mean, except maybe for limits checking, but it is not involved in the actual processing of both blending and of naive cam detection, because that is handled by downstream components. Okay. That is why we need look ahead. It's for performance and for smoothness of motion reasons, and particularly with cam packages. Now, isn't that great? We just invented look ahead, and the sun keeps shining. It's all wonderful. Unfortunately, well, it also introduces a set of new problems, and we'll get to these now. There's a catch. You remember I emphasized the position prediction thing. The interpreter must know that at all times. Well, mostly it can. For the trivial cases, a G0, a rapid, a feed move, circles, arcs, NURBS, and so forth, that's all easy. It's very easy to predict. It's basic computer graphics and geometry. But there are a couple of G-code operations where which make an exception to that. And the three violators in the current code base are probe, tool change, and reading a help pin through the motion component. Why is that? Now, a probe is a command where you give a distance vector and the tooltip starts moving until some contact closes. Okay? And because you want to determine the distance, say, from a tool switch. or a workpiece. Now, of course, you cannot tell in advance where the switch will close, because that's the very purpose of a probe operation. You want to find out. What the probe operation does is, once the probe switch closes, it warps the current point of the machine to where the switch closed. Okay? So it's quite obvious that breaks position prediction. The interpreter cannot tell because it can't tell where the probe will trip. Okay? And hence it cannot say where the new endpoint is. And the way it is implemented, if the probe switch closes, that becomes the new current point of the machine. And if you now do a relative move in G91, the interpreter would have to give an absolute endpoint to canon, because canon has no clue about relative moves. The interpreter needs to know the absolute endpoint, but there's no way to do so because the hardware didn't tell him. Okay, so probe breaks position prediction. The other commands are changing the tool. That changes tool geometry and the tool tip, and it also might involve a probe operation. So again, that breaks position prediction. And the third one is reading a hell pin through the motion hell pins. There are a couple of pins which you can read through the M67 and M68 commands. And that's kind of tricky because it's not quite obvious why that is the case. Now, imagine for a second you use if-then-else control structures. Our G-code interpreter supports that. And you use the value of a hell pin, which you just read with one of those commands, to decide whether you take the if or the else pass. Well, it's clear that the value of the hell pin determines which code pass is executed. Again, that leads to reading a hell pin breaks position prediction. So these three cases interfere with read ahead. Okay, that's why we call these commands queue buster operation, because they kill the motion queue. The interpreter cannot go on beyond them. Once it finds a queue buster operation, a probe, a tool change, reading a hell pin, it needs to stop. It cannot read further G-code commands and emit canon for them. It must now wait until all the whole motion pipeline downstream, all the way to the hardware, has drained, and the machine has executed. And once that happens, then the interpreter will call on a canon method through the so-called sync method, and the operation is called syncing. It's a method of maybe 20 lines in the interpreter. I just looked it up this afternoon. It just pulls the key position variables, offsets, current point, feeds, and so forth, from the hardware status, really, from where the machine status is tracked. We call that part the world model. Yeah? So it needs to stop after a queue buster. It needs to wait until all the commands have been drained and executed. Machine has stopped moving, and then the interpreter calls the sync method and gets the current status of the machine. And that's where it gets everything. The current probe, which is the result of the probe operation, the tool geometry, any probe results in the tool change process, and the current pin values of the motion component. And now we're again in a consistent state between machine and the interpreter's view of the world. Uh, that is necessary because if it would not do that, the next move would be wrong. It is not possible to go beyond that point. So there's no way around it. The not so nice part is that this queuebuster operation may cause a hiccup in the motion. Now, for probe and tool change, that isn't really an issue because these are very strong hiccups indeed. The tool change can be quite a complex process until it's executed. It may involve external component. So if the tooltip comes to a stop, well, it better does so. So it's not an issue there. With a probe, well, it needs to stop, start the program, not an issue either. Needs to change the feed to the probe feed, fine. But it is an issue with the hell pins. If you keep reading hell pins motion synchronized, every time you do that, the interpreter needs to sync. So it stops read ahead and then it starts again. And maybe you've observed that, but if you do motion pin reading a lot, you might get an uneven pass. Okay? So that's where these two phenomena are connected. So we need read ahead, some for performance, but there we cannot always do it, especially with these queuebuster operations. And we need a special flow of control once we hit such a queuebuster operation to get the interpreter into a state where it can continue, okay, in a consistent way where it can go on predicting the endpoint of the next move. That is the key thing in understanding. If you get your hands in the interpreter, once you have understand that, the rest is peanuts. It's very easy. It's just parsing text, simple arithmetic. It's not very complex. But that model took at least me a long time to understand because it really is not documented very well, or not at all to be exact. Yeah? That's read ahead and queuebuster operations. They break queuebuster operations in a nutshell, break position prediction. So that's why the motion pipeline stalls, and if it starts again, you might get a hiccup. You only really see this with hell pin reading, so be cautious with those. It might look elegant, but it might impact the motion result in a way which you would not like. So we're warping back to APIs for a second and look at how the read eval print loop now actually looks. Now we know all this stuff about read ahead and queuebusters. Well, since we have the prerequisites, we'll look at the methods of the interpreter API. There are about 50 or so. We're just looking at the 3 most important ones here for the purpose of a discussion. Okay. First, the interpreter is a set of subroutines. The key ones are read, execute, and sync. There are other ones like open a file, close a file, gobs of others. We don't care about these because we're taking a high-level flow-oriented view at this point. And read and execute, well, those go straight back to your paper tape reader from the late 70s, because those were called alternatively read the next block, move the machine, and so forth. So the interpreter, as we have it, does not have its own read eval print loop in its intestines. It's actually a set of subroutines which are supposed to be called from the outside. So every time the interpreter is operated in any context, in mill task, for generating preview, for generating standalone canon, as we've experimented with, there is a little main program around it which calls these methods because it doesn't have its own inner read eval print loop. So that's a legacy. We talked about reading. That's the parsing step which we we had in the first step, scanning for tokens, doing syntactic analysis, and parse the result in an internal structure. Execute means generate canon command for that current block. Okay, so execute emits the canon calls for what we just read. And sync does what we need with when the interpreter starts up, and once it has observed the queue buster and has waited until the canon, the motion pipeline has drained, then it executes a sync call. And that goes to the hardware status and pulls all the pertinent parts. Now, what is to be done? These subroutines communicate what to the calling layer, what needs to be done by means of return codes. There are about 6 or so, which you find in this link, which I'm currently hovering over. Of course, there's the error return. If, for instance, a syntactic error, that's not the totally interesting case. We're interested in the queue buster or non-queue buster, really, thing. Everything went well. Syntax okay. We're good to read the next line. And by the way, we can predict the position of the next move. In that case, the interpreter returns the value interp_OK. Okay. So in that case, you can keep going, read the next, read execute. However, if the read returns, I don't know how they came up with that name, but it's called interp execute finish. That means, we just saw a queue buster. So that was a probe, a tool change, or a hell read pin operation. And that one we need to treat special. So these are return values of the read operation. Interp error can also be returned by execute. Okay. So now to glue the logic together, let's look at the trivial main loop of a read ahead interpreter with read ahead. Once the interpreter starts, the very first thing it does is it synchronizes to the external machine state. So its worldview is correct, if you will. Okay. And then starts the read eval print loop again. As long as our return code from the next call is not, well, we hit end of file. I skipped that return code in the last slide. It's not important for the semantics. Obviously, the interpreter has to stop when it reaches the end of file, but that's not something which we're interested in here. So as long as we don't hit end of file or we're not running into an error condition, we read the next block. If we can predict the position based on the return code, if it's interp OK, we can predict the position of the move. So this is, in that case, we emit the canon commands with execute. However, if the return code was, that's wrong. That it's syntactically wrong. Drop this RC equals here. Okay, we're just ignoring the return code of execute for the purpose of our discussion. However, if the read returned interp execute finish because we observed the queue buster, well, okay, then we have something else to do. We need to observe the motion pipeline. The interpreter needs to look at the motion pipeline and say, okay, is there still stuff in there? Still stuff in there? Okay, finally it finished. The last command drained. And once that happens, we can sync, and then the whole game starts over again. Okay, so that's how it deals with queue-buster operations. That wait operation is not actually in the API. It calls upon the canon layer, which calls an inspector function to see whether there's still stuff in the motion queue being executed, or if we're done with it. Okay. So that is the core logic of the interpreter, and I think if you delving into the subject, you will find it helpful to have understood what queue-busters are about and how that motion processing fits together. Okay. Well, so much for the structural for the what interpreting canon does, and now well, we're doing fine. We can already look at in more detail on how we actually plumb things together. We have already touched upon many details, and we're just now fitting together the whole thing in chains, into pipelines. Okay, we've touched upon the interpreter, the canon layer, CAN detection. We've touched about blending and what the trajectory planner does, and that part, the hardware-sided part, that's not today's topic, but we've discussed most of this. So the motion pipeline, as it is executing a file, is really these units playing together. It's the interpreter code, which calls upon a canon layer. The canon layer might do some processing internally, like naive CAM. And once it is done with it, it emits motion commands and puts them into a queue, which is called interp list. This list is actually within the mill task process, and that is our read ahead. Okay, that is the window which we're talking about. Unfortunately, in the code, actually, the read ahead is distributed through two queues. But functionally it is one. Okay. We have not touched about this process, task or mill task. I mentioned its name. It's not important for today. The only thing, the only reason why I'm mentioning it is, motion commands pass through it because limit detection is done there. If you ask me why, I have no clue. It could just as well happen here. Fine, that's how it is. The question why that actually has to be there is, well, the reasons are on shaky grounds. Okay. So the commands are basically C structures which are filled in, put on the list. They're passed down the motion pipeline, and once the trajectory planner gets onto it, that one does the blending stuff, limits velocity, acceleration, and so forth. That also does handle live feedback commands, for instance, like feed override, or there's another override which I forgot. We'll come to in a minute. So that is actually the reason why a part of the trajectory planner needs to be part of the real-time code. It is actually the smaller part. If not for speed override and that the other override, I forgot for the moment, all that could be a strict user program. So the trajectory planner then creates segments which are strictly within machine limits already, and according to the current feed override, and that is basically a sampling stage which plays it out point by point, and the backside max velocity override. Thanks very much. Yeah, that was the other one. Both are what's called shape-changing operations because they impact on the blend. Okay. Which is why you cannot change the playout rate, but because the curve of the shape of the curves change. That is actually already quite simple sampling stage, and at that end, it's hairpins. That's the commanded position and commanded velocity pins of the motion component. Everything else from there is hell country. That drives the servo loops. That drives the step GANs. That's all stock fare. We don't care about that today. Now, I talked about the necessity that the interpreter gets a snapshot of a subset of the machine state. The current point, the feeds, the status of feed, mist, flood, and so forth. So quite a few of those. And for that, we have that back channel. Yeah, okay. The world model, the actual machine status, is collected in a pathetically large status structure called EMC stat. It's recommended reading at some time. It will turn you off in horrors because it has become a dumping ground over time. It carries this, then, and whatnot, and the dog as well. For instance, the tool table also sits there. So what the interpreter actually needs is a small subset. You just have a look at the sync method. That's maybe 15, 20 lines. It's very simple. So the amount of information which travels back here is minuscule relative to all the other crap which accumulates here. It's necessary crap, but it's a lot. Okay. Just noting on following errors. While this is not directly related to the interpreter again has no clue because it doesn't idealize pass. So it cannot possibly have any role in determining if the hardware has fallen out of tolerance with the ideal pass so much that we need to stop. And so, okay, maybe we hit an a machine limit, can't go on. Well, that's a following error too, a very loud one. So that's actually happening at that level by comparing the commanded and actual values, and if they drift apart too much, that causes an abort of the motion pipeline, and we come to a stop. Okay. So that's how the parts play together. Today we mostly covered this. We get a rough idea on how that works, but we'll keep the rest of it for the next one. Okay, so that's the motion pipeline. The tough part is over. It's all downhill from now. The easy one is preview and progress display. I put this up here because I didn't understand for a long time on how this works, because it's very arcane. In the legacy code, for instance, Axis does it that way. What does happen in the UI proper? Axis is a Python program, so that's within Axis. Okay, it does import a module called G-code, and that module, that's a C extension to the Python interpreter, that actually contains a copy of the interpreter. It links against the interpreter shared library, and it has a little bit of glue code, which does an interesting stunt. That module is called from above, from Python, if you will. It is given a G-code file or an MDI command, and what it does at the back end, it calls back into the Python interpreter. It's like, okay. Well, it does. Basically, it's called a callback. It's a slightly confusing scheme, but once you get the hang of it, it becomes natural after a while. Certainly, if the code isn't documented, it's not exactly clear on how that all fits together. So what happens? Axis calls upon that module, a method in this module, gives it a file. The interpreter executes it, and for every segment in the polyline, that module again in turn will call a Python function, and which resides in the Axis UI. So you find this Python function there, and so try to figure where is this called from. Well, it's from within here. It's one of these mysteries in the Axis code, which took me a while to understand. Now, once we're back in Python land, it's actually simple. What happens there? It's the Python methods just create emit OpenGL display list elements, which cause the preview plus the display to appear on screen. So that has no machine to deal with, so there is also no probes or tool changes or help ins. Those are not relevant mostly for the toolpath. So this interpreter basically ignores the read ahead, the QBuster problem. They say, oh, okay, let's just continue. Like a probe just is handled like it tripped at the very start of the program. And it's good enough to get a rough preview, even if it doesn't correlate to the actual execution of the pass. You'll see what it does later on in the progress display. So that preview run actually executes very quickly. It's executed once you load a G-code file, and it is done before you actually hit the run button, which is why the wireframe immediately appears. Okay, so that is how Axis and GScreen, by the way, do it. Now that's the preview part. That creates the wireframe. Now if you hit run eventually, you see the tool moving along that wireframe. Now where does that come from? Well, that is completely unrelated. It's just, I'm mentioning it just because it fits into this theme. There's a little observer thread which is in the Linux CNC Python extension, and I think the method is called position logger or logger, and it is actually a small POSIX thread which executes, I think, 10 times, iterates with 100 milliseconds, and takes samples of the actual machine position. And if it detects that the position changed, well, because the machine moved, guess what? It emits calls which can be translated into a movement of the symbolized tool head. Okay, so that's this joint, but that's how preview and progress display are generated. Notice that nothing of this has to do anything with the execution of the motion pipeline. Those are ships in the night, no relation whatsoever. Okay. We adapted that motion pipe, this preview pipeline a bit. We, in that case, being Alex and me, a little bit to cater for the remote case. Okay. We don't want our remote UIs, may they be Android phones or Windows programs, to require a copy of our venerable and well-aged G-code interpreter to create the wireframe. So we decided all this does not happen in the UI, but on the host where miltask and RT runs. So we changed the structure a little bit, but the logic is still the same. It's just that we don't generate Python callbacks here, but we generate messages which we send off over a network connection. The messages are encoded with a protobuf method package, and the transport for that is the CRMQ messaging stack, which will be the future method. Everything on this in MachineKit runs remotely on. Same thing for the progress display. The observer thread just pumps out position updates here. Okay, that is enough confusion for the day. That's 1.5 hours. That's more than I planned. I should have timed it before. But that's where I really want to stop with the material, because it might be a little bit much already for the evening. Put your mics back on. Flame me. Was that anyway comprehensible? Was it useful? Does it make sense? What's missing? What's your questions on it? Turn your mics back on.
You made it down to.
Sorry?
You made it down to.
I didn't understand that. Maybe use the chat to post a question or a comment. Oh, too easy. You mean that was too easy?
Yeah,
I'm sorry.
that's okay.
It took me years to understand this. No, that's really how it fits together. It's not all that complicated. It's just not documented. That's why I decided to start with that, because it conveys many of the key concepts already. So it wouldn't have made sense to start with hell and work back upwards. You know. Late fellows tuning in. Well, no, it can't be time zone. It's 1.5 hours. If it were off by 1 hour, it could have been a time zone error. Anyway, please tell me, is that level of abstraction and detail, is that the right one? Was that introduction on interpreter use too dumb, or should we? It was kind of hard to gauge for me to what level of detail I should drill down, and then eventually said, forget it, just go for the high level stuff for now. Well,
Yeah, well, personally, I think for me it was a little bit difficult, but I'm not a programmer, so I think for a lot of people it will make sense. But for me, it's good to understand what is happening. So I think that's for me, it's good to know what is going on there.
okay.
I don't know how other people experience that.
Same for me. I'm not a coder, and I got along with this quite good.
Okay, super. Thanks. Okay. I actually do have material left, but that is too much because I'm already occupying you for 1.5 hours, which is way beyond our planned lengths. So I will postpone the question how actually developers in Wings can contribute that to a separate session. Or maybe we'll cover it next time, but I think this is getting too much for today. Suffice it to say, that's one of my favorite websites, by the way. It's called despair.com, and they have absolutely great, they have absolutely great sujets there. And I use that because, well, we use that code since years, but frankly, a lot of that needs cleaning up. But I'll leave that motivational pitch for another time. To plan what Michael asked what to cover in talk 2. Well, we focus on the motion part of it, and G-code and canon. But there's more than to that. Ding-a-ling-a-ling. Okay. There's more to the operation of the CNC stack in MachineKit than just the interpreter and the canon layer. For instance, jogging or all this modal hell like joint auto mode or the trajectory planar modes, teleop mode, coordinated mode. There's still several concepts missing, and for the operation, if you recap the UI, any UI really, you have auto, MDI, or manual. So we didn't touch upon any of the manual commands at all today, we didn't touch upon issues like tool change, for instance. That ties in. So the next one the next talk will assume basic knowledge of the motion pipeline as we talked through it today, and provide the wrapper, basically the semantics of the miltask program, which is the controlling entity. And everybody hates to read the code, but we need to understand it a little bit what it does. How it can be used we'll use the Linux CNC module API as an example on how to talk to miltask, and I think that will be enough for the next talk, because I think I'm overdosed a little bit today because I'm running now 1.5 hours. So it's really the operation of the miltask program and how UIs talk through it through the Linux CNC module, and how that pertains to actions in certain UIs. Okay, essentially, what's behind the UI, and what information do you get out of it? That's a key thing. Actually, I wrote the documentation of that module because I didn't understand it, and that file is about 1.5 years or 2 years old. So I think before it, none of it existed actually. So I'll take that as but that is a API which remain downstream even if we refactor internals. So I think that will be a good starting point to explore the overall operation of the CNC stack, not just the motion pipeline. And we'll have to explore modes a little bit more. This joint mode, teleop, and coord mode and world mode. So that needs a little bit explaining on how it fits together. Yeah. This one was more fun than the next one, though. It is relatively complex to understand because of the modes and machine states involved. The design of the legacy code base clearly went overboard on the amount of state it assumes and calculates through all the components. That's the plan. Okay. I'm happy to touch on any issues which were not covered, which you deem important or unclear. If anything comes to your mind, say so now. We're all together. Maybe other people can profit from it. 39 people are here. Hello. Hell as a remote controller.
Yeah, like for a quadcopter or something.
Ah, I see. Okay. I plan to do that, but not the next time around. We'll do the tough. That's the fun part, okay? When you get to hell, it's all smooth sailing. Yeah. But that is not the part which we have the big problems with, but I'm happy to do one, yes. For instance, the remote operation of hell needs a little bit explanation, to be honest, documenting, right? So that's really just in the brains of Alex and me at this moment. But yes, well, once we've covered the CNC stack, I want to have that covered with the next unit. I hope I'll manage. And then we'll turn to hell-related issues. Those can be treated mostly disjoint from the CNC stack because it's a very clear distinction. We need a better chat structure. What do you mean by that?
Well, there's been a few messages about people not being able to join the chat. We are only able to be 10 people in the video call, and it seems like the group chat has a limit around 40. It says 41 right now, but they're saying people can't log on.
Oh man. Then it might have happened that they connected to the wrong URI.
No, I think this is a thing with Google Hangouts. I think there's a maximum. I think what we need to do next time, we need to look at how many people got into this in this Hangout, and I think we need to look into, for example, a Gitter where we can post some questions and answers. Because if there's a maximum and there are more people looking at this, then we need to find a way to have at least all the questions streaming in, because it will be difficult to gather all the questions and relay them. So I think that's something that the first thing we did this evening was for us also to learn how we can get better communication going. I think it's very good that we are here. But we need to find out a better way to get there, I think.
Okay. I think I'm visible. Okay. Fair enough. Should we leave it at that? I would suggest yes.
Yeah, I'd like to say thank you for the presentation.
You're welcome. It was a pleasure having you.
Thank you.
I'm happy to do the next one if there's interest. But it seems there is.
Yeah, and please, people, if there are some ideas or other stuff that you'd like to say and get some improvement maybe on the way of chatting or communicating, put it on the list. And well, let's try to get this to a better way of just some more communication. I think this is very valuable for the project.
Well, maybe the GitHub issue. Well, okay, let's either way, doesn't matter. Yeah, let's exchange our experiences and what we can do better next time.
Yeah. Well, it went okay for the first time, and I think the first time is for us to learn. For me also, because I don't get a G plus stuff at all, so that's new for me.
Okay. Fair enough. Well,
Okay. Thank you, Michael.
have a good night here.
Yeah, thank you.
Happy afternoon in the States and good morning in Asia. Not just Vietnam. Okay. Goodbye.
Okay, goodbye.
Thank you. Good night.
Good night.
Bye.